Everyone, and welcome you all. I'm Debasrita. I'm a Director PhD scholar from the Department of Electrical Engineering at Madras. So today I'll be talking about my work, already pre-published work in Sensors Journal on a planar coil based inductive bend sensor for soft robotic applications. So my talk will be subdivided into certain sections. I'll give a brief of what is soft robotics. I know it's a new domain altogether. Everybody is talking about hard robots, traditionally rigid robots. So, and then how the integration of specialized sensors into the soft robotic structures are important. And then I'll talk about my proposed work. So what is soft robotics in a sense? So it is a subset of robotic sciences which draws its inspiration from the biological organisms per se. As you have already heard the talk from Professor Bilal, that she is working with the amalgamation of soft and hard rigid robots, and just seeing the shapes, sizes, and how to just work with different objects, what is the interaction with them. So here I'm focusing on soft robotic applications, but my work is substantially pointed on sensors, how to integrate different sensors. So for example, if we want to grasp an object with a human hand, because I said soft robotics draws its inspiration from human or living organisms. So if I want to grasp an object, so there's a whole lot of network going on inside. So my hand will touch the object, it will sense what type of object is it, it sends a signal to my brain, and then it will say that how much pressure it needs to provide to the object to grasp, or how much bend angles it needs to bend to grasp that glass, or if any circular object, some cubic object. So we need specialized sensors to sense those parameters. So there are different sensing parameters. We are here focusing on bend angle parameters, how to measure or sense bend angles of soft robotic structures. Now there are challenges to soft robotic structures, is that we need specialized sensors so that it doesn't affect the mechanical behavior of the soft robotic structure, because as compared to hard robots, they have rigid parts, they have rigid joints, so we can actually model them. But in soft robotic structures, they bend at different bending angles, a continuum bending is happening. So we need specialized sensors, flexible sensors, which takes the shape of the object, and on the other hand, it doesn't affect the mechanical properties or behavior of the structure. So this kind of soft robotic structures are made up of mainly elastomers, polymers, mainly silicon. So there are available sensors. Different groups have proposed different sensors, but out of them we have chosen inductive sensors to work upon, because they provide, as compared to other sensors, they provide good repeatability, good hysteresis, less hysteresis error, and they are they're not that much sensitive to humidity, dust, temperature variations, etc. So we have focused our work on inductive sensors. So my work is actually focused on development of inductive bend sensors to find the bend angles of a soft robotic finger. So this is my proposed sensor design. It has already been published in Sensors Journal, IEEE Sensors Journal. So to give an overview of the sensors work, sensor design, and how the integration is happening. So this is, sorry. So this is a gripper, and each arm of the gripper is a soft robotic finger. We introduce our sensor, that is a collective package of collective package of flexible PCBs. So we introduce the PCBs, a set of PCBs in a base chamber, which is easily detachable and replaceable as well. So in the censored part, what we have done is that we have packaged three flexible PCB layers. In that, if we talk about one censored unit, so the middle layer will comprises of all the primary coils, will energize this primary coil, and the top and the bottom layers consisting of the secondary coils, and through which there will be mutual coupling, will energize the primary coils. There will be mutual coupling between the primary and the secondary coils, and will take the secondary voltages out of both the secondary coils. So what happens is that when we actuate a soft robotic finger here, the sensor introduced in the base chamber also bends, so there will be a non-overlapping area introduced at the edge, as well as there will be relative displacement between the coils, like that. If it is not actuated, the coils will be straight. The mutual coupling will be initial mutual coupling. Once it bends, there will be a relative displacement between the planar coils. So that relative displacement we have used to measure the bend angles. So this sensing scheme has already been published, and we have granted patent on this design. So here what happens is that we'll energize the primary coils, but the main thing is that one of the primary coils will put a current flow in this direction, maybe a clockwise direction, and the next consecutive primary coil will allow the current to flow in the opposite direction. So what will happen is that when the secondary coils, which are initially without any actuation, they are equally influenced by both the primary coil current. So there will be the net flow, magnetic field will be zero, and there will be no secondary voltage initially available. Now, when there is a relative displacement due to the actuation of the coils, actuation of the finger, and also there is relative displacement between the coils, what will happen is that one of the primary coils, secondary coils will move to one of the primary coils. Other secondary coil will move towards the other primary coil. As a result, the secondary voltage will change. So we have done a finite element analysis using console multiphysics software. So, and here we can see that upon the displacement of the coils from towards any one of the primary coils, for one of the secondary coils, it increases. For the other, it goes down, because we have the current direction is opposite in both the coils. And as a result, it shows a push-pull pattern of secondary voltage. So that we have used to as a measurement as a parameter to quantify the bend angles. This is a measurement circuit that we have used to actuate our system. So these are the planar coils, flexible planar coils. This is the data acquisition system that we have used and a PC to demonstrate our results. This is the developed prototypes that that we have. This is actually the sensor, prototype bend sensor. And what we have done is that we need a reference to find that whether, okay, our sensor is giving the correct bend angle values or not. Now, we have made a 3D printed structure with groups of reference bend angles ranging from 0 to 50 degree. And we have introduced our sensor at each groups, and we have found out whether the results are matching with the finite element analysis results that we have got, and whether it shows a push-pull behavior or not. For one of the secondary coil, the sensor will secondary voltage will increase, the other will go in the opposite direction. So these are the results that we've obtained from the sensor output introduced in those groups only. And we have, because we have got a push-pull kind of results, so we have done a ratiometric analysis, ratiometric output. So we have obtained a ratiometric output from those secondary voltage values, and which shows a linear behavior. So then what we have done is that whether it can actually give the secondary, the bend angle measurement of a soft robotic finger or not. So we introduced the soft robotic finger with our sensor in the base region here, like that. Here, this is the sensor group of PCBs, and then we have bent the soft robotic finger at different reference angles, and found out the resulting secondary voltages from the two secondary coils, from the two upper and the bottom PCBs. So this is the ratiometric output that we have obtained here, and you can see it shows a good linearity with R-square value of 0.9963. And we have also seen the dynamic characteristics, both secondary voltages and with the ratiometric output. We have manually actuated and done continuous relaxation and actuation of the finger and soft robotic finger like this. And this is a manual actuation, so there will be some variations there, this part, but as because this is a manual actuation, but the pattern is almost same that you can see. So it shows good repeatability, and sensitivity is 0.003 per degree, as because it is a ratiometric output. Yeah, so these are the comparison tables. So comparing with other available sensors, our sensor is a linear and shows good sensitivity, and the cost is also minimal. This is the conclusion. I have developed a flexible planar coil based bend sensor with a limited, and it uses the relative displacement between the two planar coils with a constraint of limited space available. It shows linear characteristics with good sensitivity and resolution. These are the publications that I have. Thank you.